Very well. Before we start, I will do a short introduction. Do you prefer that the questions are asked during the
Sure,
presentation
that's
or
fine.
in the
Yeah,
end?
that's fine.
Okay. Okay. So in the end, if we have questions from YouTube, I will read them to you in the end. Okay. At the end. Okay. Very well. Okay. Well, I think we can start. People will still be joining us. And well, let's start. So first of all, hello everyone, and welcome to another talk in our webinar series. Today we have the pleasure of having Dr. Dragan Huterer from the University of Michigan. His principal interest is in understanding nature and origin of dark energy. And today he will be giving us an holistic view on probing the universe with the Dark Energy Survey. So before we start, a quick reminder that this webinar is also being streamed live on YouTube. You can find the link on our website or access it in our YouTube channel, LIneA CTI. Dragan, thank you very much for being with us today. The floor is yours.
Rodrigo, thank you very much. Thank you for your invitation. It's a pleasure to be here. I'm Dragan Huterer at University of Michigan. I'm a theoretical cosmologist working at the interface of data and theory. And I will say a few words about some results from Dark Energy Survey. Some of you have heard some of this, but maybe not all of you have. And maybe you haven't heard the relatively recent developments this year. So I'm going to talk about that. I will not have a chance to talk too much about DESI, another big survey that some of you are part of. DESI is a spectroscopic survey, unlike DES, which is photometric. And actually, just last night, I think, I got an email that DESI had a record night with 137,000 redshifts in one night. Now, this is really hard to comprehend, at least for me, 137,000 redshifts in one night. So DESI is rolling along. And that's exciting. But here, DES, of course, is at a much more advanced stage of data analysis, and so you know, science results. So I'm going to talk about that. This is a view of Blanco Telescope at Cerro Tololo in Chile. And so I hope you can see. I switched to the next slide. This is a basic picture of. This is a Hubble diagram. It's a simple picture, yet it's actually real data. The y-axis is the distance modulus. It's a measure of distance as a function of redshift. And you see some data points. Black data points are supernovae. They're binned in redshift. So every data point is about 20 supernovae averaged, represented by. If I didn't average these data points, the errors would be big and they would be all over the place. And then you see some cosmological model. The one that the data favor is the one that accelerates now, decelerated in the past. You also see in green color the open and flat and closed models, or representative of those models for various values of omega matter, and you can see that none of them fits the data. Now, to be fair, in this plane, it turns out you can shift vertically the theory relative to the data. So the vertical shift is allowed. So it's not as extreme as it looked. It's really the shape of this curve, of the blue curve, that's favored relative to the shapes of the other curves, you know, because normalization is free float. And so this is visually the evidence for dark energy. And maybe it doesn't look super strong. In fact, if you squint by eye, you can almost convince yourself that green curves could be made to go through this data. But they don't. And you can see that the supernova data, they exhibit some degeneracy in this plane between omega matter, the amount of matter relative to critical, and the equation of state, P over rho, of this new component that was found, the dark energy that makes the universe accelerate. CMB and large-scale structures, surveys, baryon acoustic oscillations, these three curves intersect around the value of W minus 1 and omega matter about 0.3. Now, during my career, I observed these error bars, especially on W shrink, and they've shrunk around this very special value of minus 1 that represents vacuum energy. This is also an interesting plot from this, also from this review paper I wrote with a former student, Schaefer. That same plane, but data 20 years ago in green, 10 years ago in red, and roughly present day in blue. And you can see that the data shrunk around this value of W minus 1. So this tells us that matter is about 30%. In a flat model, dark energy is there for about 70% of the critical or the total, and then P over rho of dark energy is about minus 1. Now, I mentioned that the data, they're actually much stronger than they seem by eye sometimes, and this is an incredible fact that just a few years ago, if you just take the basic data sets and combine them, you get 72 sigma evidence. So by now, it's surely 100 sigma evidence for dark energy. So in other words, the result omega lambda is 0 is almost like 100 sigma away from what the data favor. And at that point, it doesn't even matter what you assume for the equation of state of dark energy. There's incredibly strong evidence that universe is accelerating, or it makes it look like it's accelerating. So something is going on. It's maybe 20 years ago, it was a possibility that supernova data just, maybe I don't trust supernovae, maybe they have some issues. But that was nowadays, even if you completely disregard supernova data and throw them out the window, if you say, I don't believe anything that supernova tell me, just because from other probes, there's still very, very strong evidence for the accelerating universe. Then the question is, how well should we do in P over rho? Now, this is a tough question because unlike in some other areas of physics, we don't know. We don't know how well we need to do in equation of state of dark energy. Contrast this with situation in two other famous scenarios in physics. One of them is in neutrino masses. So from neutrino oscillations, we have two values for delta m squared, the difference in the squares of neutrino masses, of something like 10 to the minus 5, 10 to the minus 4, and a larger value for atmospheric. And it turns out you have three neutrino eigenstates. There are two mass differences. So there are many solutions. And assuming the lightest eigenstate is 0, so under some simplifying assumption, you find two possible solutions, the sum of the masses being 0.06 or 0.11 eV. So these are the two values. In fact, we think in our universe, the least possible sum of the masses under any scenario is this, 0.06. We think they cannot possibly be lighter than this. The sum can be larger, it can be 0.11, or it could even be more if M3 is not 0. So this gives us a very precise target. Future surveys should ideally be able to distinguish between the hierarchies. In other words, they should be able to measure the sum of the neutrino masses to much better than this difference, which is 0.05 eV. So that presents a very, very concrete target. And for example, DESI plus Planck will be able to measure that, maybe not at 5 sigma, but 3-ish sigma or so. So it has a chance of distinguishing. We don't have that target for dark energy. The other famous example is Higgs boson mass. So from various top quark and W boson measurements and their widths and rates, it was known already that something like Higgs mass, before Higgs boson was discovered, it has to exist, and its mass has to be less than ballpark 200 GeV. It has to be, if it's much bigger than that, there's a huge problem. And indeed, it was found. Again, that's a target. You know how to build your experiment in order to find it. And again, we don't quite have anything like that for the equation of state of dark energy. So in addition to that, there's, I think all of you have heard, even if you're not in cosmology, of the most famous, and I think justifiably so, current tension in the field of cosmology, Hubble constant, difference between 74, a higher value implied by local measurements using the distance ladder, based on supernovae and Cepheids, and a lower value favored by the CMB and isotropies, which happens to measure H0 very accurately in a way that's not completely immediately intuitive. And even though these two values don't seem very far, remember, historically, there's been an argument between 50 and 100. Now it's converged to about 70, but within the error, this is actually about almost a 5 sigma discrepancy. And I think this is a very exciting development. It may indicate new physics. It may also indicate some systematics, but we are not sure. Right now, there are no suspects among the systematics. So it's still very much possible that this indicates new physics. And these are visually some of the measurements. I mean, these tables are not always super helpful. I think this split into early and late measurement is not necessarily super accurate. The main thing to see is that lower H0 comes from CMB, higher H0 comes from local distance letter measurements, and then there's some other probes, particularly gravitational lensing, weigh in with somewhat larger error bars. So this is going to be a very interesting thing to see in the coming years, how Hubble tension evolves. There are many surveys to understand dark matter and dark energy, especially. Many of them have the word dark energy in it. These are just the biggest surveys. There are many that I didn't mention. These are just the most famous ones. I'm going to talk about DES. I mentioned briefly DESI. These are the photometric ones, the spectroscopic ones, and then the two famous space telescopes, Euclid and WFIRST. And they're going to be really good, and all of these will inform us about dark energy, as well as these other things I mentioned, like the Hubble tension. Dark energy survey is on this telescope in Chile, the Blanco Telescope. It's a big camera. It finished its observations already in 2019. It's 5,000 square degrees. It's quite a big chunk of the sky. This is the footprint on the sky. 5 bands, goes down to some magnitude. And it's already measured positions and shapes of multiple hundreds of millions of galaxies. I'm going to just go very short on the DES. This is a camera now. I'm a theorist. I'd actually never gone observing anywhere in my life prior to a couple of years ago. But then I got a chance to go observe for DES. This is Cerro Tololo. These are some of the pictures I snapped. This is another student taking a picture of me looking serious in front of 8 screens. To be honest, I had no idea what I was doing. I was, I was a bit lost. But there's a very nice software called OBSTAC, Observer Tactician, that some people wrote that makes you, but at this point when I was there, it was automatic. You just run this software. There are very nice instructions, very easy. You can read the book the rest of the night. It's observing. You look at the screen, you make yourself coffee. There's a kitchen behind. And so it was really easy sailing by the time I was there. So I really was quite lost, but it was a pleasure. And this is a huge structure, this building in which telescope is housed. This door is size of a large truck, and the size of the person is maybe like this much. So it's a really pretty big, impressive structure where this telescope is housed. If you're a theorist, I highly recommend you go observing if you haven't. Very good experience. Many participants, DES is like 500 people or something like that. Not all 500, but to the analysis, at least 100 contributed. These are some of the names. The early career scientists are in bold. Many contributed. Some of the people on this call contributed. My contribution to this was not huge, but I was joined. But I highlighted here the names of Elizabeth Krause and Michael Truxell because they were science coordinator overall and science coordinator for year 3, and they were really adults in the room who, in addition, they did 2 things. They did a lot of coding and scientific work, direct scientific work, and they did a lot of management and had to do a lot of people skills. And so they really did massive amount of lifting on 2 fronts. So I wanted to highlight that. I'm a theorist. Most of my work in the past was on few author papers, and this was my first major experience with large collaborations. There are some pros and cons, but one thing I can tell you is for those of you who haven't been as a part of a big collaboration, some of these papers are really massive amount of work. Not that any task is hard, it's just that there are too many things to do. And so that's why you need a big team. There are a bunch of papers, a lot of maybe even too many papers, like 29 papers in year 3 release. But most of us don't really have time to read 29 papers. So one of them is really the key paper that takes from all these input papers and combines into cosmological constraints, and also reviews all the technology that's been developed. Again, if you just look at the list of these papers, you realize that this could not be done with a smaller team. This is the key observable in the DES analysis is what we call 3x2 correlation function, because it's very important. I'm going to review this in one slide, and this is a very important slide in case you don't know already what 3.2 is. So there are 3 kinds of things you can look at. You can look at the clustering of galaxies. So here's observer, here's the galaxies, here's the background galaxies whose shapes are shared by foreground large-scale structure. You can just look at the clustering of foreground galaxies. This is this G term, That's galaxy clustering. You can look at the clustering of shears in the background. This is this SS term where shears are clustered with other, you correlate shears. And then you have the cross term where for each foreground position, G, you correlate that with background shapes S. So this is this cross G S term. Now, if all you had was one redshift bin and one angle bin, one theta and one redshift here, one redshift here, you would have a 2x2 matrix. And you'd have three measurements, one GG, one GS, and one SS. But because there are several redshift bins in the foreground and several redshift bins in the background, so you can do permutations of all possibilities, as well as multiple angle bins. This proliferates. So what we call the data vector, which is a combination of these GG, GS, and SS, is about 1,000 long. So there are about 1,000 measurements. Once you take the multiplicity of various angles and various combinations of redshifts, and this GG, GS, SS, it's about 1,000. Then, as with any measurement in physics, you have a question: what's my covariance? What's my error bar? What's my covariance? The covariance is given here, and this is the single most difficult thing to do when in theory model is produce the covariance. It's a subject of a lot of work. It's mostly theoretical. You may think, that you do it from simulations, but you would need a lot of simulations to have such a big covariance and be able to invert it. So it's really mostly theoretical. You can see the different bins here. Psi plus and minus are shear. W is galaxy clustering, and gamma T is that cross term, galaxy shear cross correlation, which has a horrible name, galaxy lensing. And if you line them up, you can see that they're correlated. And in fact, these small divisions are different, I think different angle ranges or different redshift bins. So, and like I said, the total length of this matrix on each side is about 1,000. So this covariance matrix is a key input that goes into this analysis. So we have a total of 32 parameters. Why do we have so many parameters? That's a lot of parameters. Well, we have like 6 or 7 cosmological parameters, but then we have a whole bunch of astrophysical parameters that are nuisance. That is to say, we have to marginalize over them in order to do the analysis. And some of those parameters have to do with biases, and others have to do with some nuisance factors that are simply not known a priori. Everything is validated. Validated means double-checked. There are 2 lens samples, Red Magic and Magnum. I'm going to talk about them briefly. There are 2 codes doing the analysis. There are 2 models for intrinsic alignment. There's kind of 2 of everything, 2 or 3 of everything in order to double-check and validate this. And that where a lot of the work goes in this multiplicity of analysis kind of ways in order to be sure we are doing the right thing. And results are blinded. I'm going to say a few things about that in a moment. In fact, I'm going to talk about blinding now. Our requirements are to preserve. So you can blinding is something that particle physicists do. Don't look at your results before you're done with the analysis. Otherwise, you bias yourself. And you can blind by not looking at the axes, not plotting the axis values. Or you can do a more sophisticated thing. And by far the most general blinding procedure, I believe, has been done by the DES team in this Muradol paper, where we said we want to preserve internal consistency of probes and check for systematic. So we want to blind, but we still want to look at the data just without knowing parameters. So this is like a long paper that took 3 years to write where we do this. But after some searching, we arrived at this proposal where if you take some observable, say psi ij, so psi is a correlation function of shear in between bins I and j. You take the measured thing, which you don't want to look at, and you get the blinded thing by adding the difference between 2 models. So this is, for example, lambda CDM model, and this is, for example, WCDM model. So I'm not going to go into that in detail, but if you think about what this does, if you just added an amplitude, a number to this, it wouldn't work, because the blinded, if measured cosmology if measured thing correspond to cosmological model, blinded would not, if you just added an amplitude, or if you multiply by a number. But if you think about what this does, as you add the difference of 2 cosmological models, then if a measured thing is a good fit to some theory, for example, blinded will also be preferentially a good fit to some other theory. So this, anyway, long story short, this prescription satisfies our requirements, and there's a 30-page paper validating this blinding procedure. This is the data from year 3. I think many of you have seen it already. It's not particularly new. It was published in May. As a function of angle, this is cosmic shear. So this is correlation between shear and shear in different. So these two, in the real space, there are two shear functions, xi plus and xi minus. So you have to look at both of them. And let's look at, say, one of them above the diagonal. So the numbers here show the foreground, the two redshift bins. So you have 4 bins, and you have, for example, galaxies in bin 1 correlated with the shear of galaxies in bin 4 as a function of angle. There's the data. The line is a lambda CDM theory, and the shaded regions are what we did not use because we didn't trust our modeling on small scales. So small scales are thrown out, and you can see we throw out quite a lot of points. That's shear. This is the same for galaxy-galaxy lensing. This correlation between foreground positions and background shears. And then galaxy clustering, we just do the autocorrelation. So we don't do the cross, we just do the bin 1 with bin 1 and bin 2 with bin 2, etc. Again, the gray region is not used. So these are the measurements. The total number of data points left after the cuts is about 500. I'm going to jump through 17 other things I could talk about, procedure analysis, but it's all fairly standard. I'm just going to jump to conclusions here. These are the results. Cosmic shear and combination of galaxy-galaxy lensing and galaxy clustering. Turns out you can look at the two separately. And these two have about as much power as the shear. They generally agree, and they give you a result omega matter is about 0.3. And this S8 parameter defined in terms of sigma 8, the amplitude of, this is amplitude of fluctuations scaled by this. So this is the combination that largely structure measures pretty well. It's measured to be 0.755. So in fact, these are the numbers. This is the S8 measurement. This is the omega matter measurement from DES alone, and sigma 8, if you like, the error bar is bigger than S8. And then if you allow equation of state to vary, you get slightly bigger error bars. So the results are in line, they're consistent, they're in line with other lensing probes, and they are comparable to the best lensing probes to date. I can say more about that if anyone cares, but that's the bottom line. Now, yeah, and if anyone has the questions, feel free to interrupt me. I'm not in a hurry anywhere. I've been skipping a ton of details here about the analysis. I mean, it's fairly standard. If I had more time, I would talk about it, I can say, but I've just jumped to results here so I can talk about some other aspects of DES and other things. But the cosmological result, this is a product of several years of work, and it all culminates basically in this slide. But by work, I should say by 50 to 100 people, at least something like 100 people doing analysis. Now we saw one anomaly in our data that I'm going to talk about now. People like anomalies, I do at least, because they may be signatures of systematic errors on new data. And in order to talk about that, first let me talk about our lens samples. So there are two lens samples. One is called Red Magic, one is called Maglim. Red Magic is small, they are subdivided into redshift bins, both of them like this. Red Magic has better redshifts, photoz's, but smaller number of galaxies. And Maglim has more galaxies, much more, like 2 times more, something like that, but worse redshifts. Okay, so you trade off here, you have a bigger number, but you have worse photoz's per galaxy. And we had both in the game, but one of these, they differed in one respect that I'm going to talk about next. First of all, let me point out that our combined result from 3.2 is extremely robust. And I think this is really true. I don't like exaggerating such claims, but this is really, really true. If you, for example, look at the fiducial Maglim analysis and Red Magic analysis, they write right on top of each other. So they're robust in other aspects as well, but this Maglim and Red Magic for the combined result, 3.2 is robust. What hasn't been robust is if you break it up into pieces. So I'm going to talk about that now. So if you break it up into pieces, and if you look at separately, separately shear and this combination of galaxy-galaxy lensing plus clustering. So this separately, that's the one case where Red Magic seems in. So if you look at the total, all the ellipses I plotted here, you can see that one ellipse is clearly disagreeing with all the others. That ellipse that's disagreeing is the Red Magic, this combination of galaxy-galaxy clustering plus galaxy-galaxy lensing plus galaxy clustering, so gamma plus W combination. For that combination, you get different result than for cosmic shear from red magic and of anything else for that matter. And so while that's true only for this split, still the question is, why does this happen? Why is this constraint really quite far away from the rest? So again, it only happens in red magic, and it happens when you do the split into shear versus these other two things. Well, we don't know why it happened. So after we unblinded, we spent 4 months trying to understand this, and we don't have a killer explanation for it. So it's a really tricky, it's most likely a systematic, probably a systematic, something to do with galaxy selection or something that we haven't been able to identify yet. We can describe it phenomenologically though. Here's how we have one parameter that describes this difference. To explain that one parameter, I have to remind you of the definitions of the galaxy lensing and galaxy clustering. So galaxy clustering is just bias squared times matter clustering, times matter 2-point correlation function. And galaxy lensing, remember, it's cross correlation of galaxies and shears. So you have also matter power spectrum times 1 power of b. You only have 1 power of b because you are correlating galaxy positions with shear, and shear doesn't have bias and galaxy positions do. So here only you have 1 power of b, you have b squared. So that's a normal formula. And in order to explain this weird result, this lowness of what we call 2 by 2, this gamma plus w, we introduce a new parameter called x lens, whose value really should be 1. So this is a completely phenomenological parameter. It doesn't have any physics explanation. The thing is, this one parameter set to a value much less than 1, so it's 0.87 plus minus a smallish error bar, explains this data. So in other words, we are breaking the relation between these two functions, making gamma smaller than the corresponding w. And this error bar here, I think, is maybe for one of these 2 by 2 only, but when you do 3 by 2, we detect X lens less than 1 at 5 sigma. So we have a 5 sigma detection of some nuisance parameter that basically just encodes this anomaly. I hope that makes sense. So it's something, probably some systematic, but that's actually one thing that came up. And because people like anomalies, I'm talking about it. We've tested a ton of things. In this Pandey paper, you can find some of these tests. And if you look at the parameters omega matter, S8, and the bias, the shaded region is the fiducial result. And the thing that stands out, that sticks out, is this 2 by 2 result. So 2 by 2 again means it's gamma plus W, lensing, galaxy lensing and clustering. That thing is off. So the S8 is high and the bias is low. And if you look at all the other bars, if you try only small scales or only large scales, if you try messing with the fiducial result, it's complete. All of these error bars agree. So if you do any kind of try a simpler model for intrinsic alignments, try dropping redshift bins one at a time. Like I said, try larger and smaller. Try changing cosmological parameters to WCDM to none of them really explain this deviation. So this deviation is not due to any one bin being wrong, to neutrinos being fixed or forgotten, to large scales. It's some other more systematic thing, so to speak. Something have to do with the galaxies in red magic that we don't fully understand yet. But this is also somewhat reassuring, although knowing that we couldn't pinpoint the systematic, it's reassuring that the data are robust with respect to all kinds of variations. Foregrounds are one immediate possible suspect for this, and this is something I've worked on over the years. I'm going to talk about foregrounds. Maybe some of you don't worry about large-scale structure foregrounds, not familiar. This is how you think about large-scale structure foregrounds. You can have, if you're on a mountain, not in space, you have air above you, so there's air mass effects. There are all kinds of subtle effects. There's stellar density. So for example, if you have large amount of stars, you can see galaxies very near stars, my observer friends tell me. So you have to avoid regions very near stars. So if you have lots of stars, you will mistakenly avoid galaxies in that chunk of the sky. So you'll find the artificial underdensity of galaxies just because there were stars. So there are subtle effects like this that happen in large-scale structure Their foreground contamination, sometimes it goes under different names, calibration errors. They are kind of visible by eye, and the one thing you see over and over again is they affect large scales. So the large scales are affected by these errors. So if you don't do any cleaning of the errors, you're going to get wrong results. This has been known for a long time now in large-scale structure. And we do this, this Rodriguez-Monroy paper does this. We have a kind of a convoluted way to do this cleaning. It's not the simplest one to understand. So maybe I'll explain this only if somebody asks. But it works. This is a very good method. It's just kind of clumsy to explain. It's iterative. But we do clean this. And in fact, here's what would happen to galaxy clustering if we didn't clean it. So here's a galaxy clustering theta times W theta times theta. Red points would be our measurements if we didn't do this cleaning of the systematics. And the black curve is when we clean. The black curve is the theory. The green points are when we clean. And you can see at large scales, at large theta, you lower the power, right? So that's what I said. These systematics are adding power at large scales, and there are sophisticated methods to remove them. So we do that. In fact, my former student, Noah Weaverdick, who is now Chamberlain Fellow at Berkeley, he's a leader in this field, in my opinion. And he and I had a paper where he studied these. So take a look at this plot. This is when you clean them, some fake maps with some templates. The vertical axis is the error, delta chi-squared error. So you want the vertical axis to be low. So, and the horizontal dashed line is you want to be lower than that. So you have various methods here. This is all kinds of methods to clean systematics. If you don't clean, you get huge delta chi-squared. If you clean, you get lower and lower. And you can do very naive things. You can do better and better things. The DES method is the one called DESY1. It does pretty well. Even if you overfit, if you do overfit, because you're fitting with some templates, you do pretty well. And Noah developed his own method. Here's which has some very nice properties, which is this elastic net method. So anyway, we thought, even though we did clean, we thought maybe this surely may be a problem. You know, we didn't. This cleaning is always kind of a suspect. It turns out it's not the reason. So after much work, we found that this really is not, the foreground cleaning is not the reason for this excellence anomaly. It's something else that we don't fully understand. Overall, some thoughts about this kind of analysis. Some of you are maybe thinking of joining surveys, or maybe you've joined already. So photometric large-scale structure is, this sounds a bit of a cliche. I think it's hard. There's a lot of headaches always. If you're used to cosmic microwave background, this is much dirtier. You have to worry not only about galaxy bias, about these foregrounds, and there's lots of kind of somewhat of a dirty work, I would say, at least to a theorist, that needs to be done. And photometric redshifts are hard. Yep, that also, and also nonlinear scales. So I think these two things, photo-Z's and nonlinear scales, they're difficult to model. This might be a purely theoretical question, even at some level, modeling nonlinear scales, but it simply is the case that we have to depend on numerical simulations to model them, and simulations are not perfect. You know, simulations don't agree with each other. So as you go to fairly nonlinear scales, that stuff. What DES did is basically throw out most nonlinear scales. So be very conservative in throwing out scales. In the future, we'd like to use some of those scales, but that requires clever modeling. So those are the hard parts. The nice things are there's a lot of information in large-scale structure because of the 3D, and also their shapes and positions of galaxies. And in particular, there's information both about the geometry, about distance and volumes, but also about the growth of structure. And so this is a really nice thing. And this is why we, I think this is a reason to be excited about large-scale structure, despite these difficulties and challenges I talked about above. So speaking about geometry and growth, let me talk about comparing them. So if you, if I look at the Friedman equation with dark energy, I have expansion rate squared is equal to, this is a Friedman equation, basic equation from cosmology. I have dark matter and visible matter, and then I have a dark energy term. I wrote dark energy term in a weird way. And the reason I wrote in a weird way is I can move this term to the left-hand side. And if I move this term to the left, I get this equation, which is the same equation, but with only matter on the right-hand side and a weird expansion history which I can say it's modified gravity. So this is kind of the difference between modified gravity and dark energy. There's no way to distinguish between these two possibilities, even in principle, if you only have expansion history measurements. In other words, if you measure h of z, h Hubble parameter as a function of time to 20 decimal places, you still cannot distinguish between these two possibilities because they're mathematically identical. But you can potentially distinguish between them if you measure the growth of structure. Here's the simplest equation for the growth of structure is a second order ODE. And now if you measure Hubble parameter, you can solve this equation. You need to know rho matter for the growth. This is delta rho over rho. So you can solve this equation for delta. And so you have a prediction given GR for the growth of structure for delta of T. And now you can go and actually measure delta of T. So this is, you can predict it just for measuring expansion rate. And then you can measure it separately and decide, does your measurement for the growth match this equation? If it doesn't, then in principle, you've ruled out GR. So this is the really nice kind of intuitive picture to me. Combining expansion history measurements and growth measurements, you can kind of break this degeneracy in you know, if about modified gravity. There are some details about this that are not so clean, but at least I hope at the general level this makes sense. Our approach and other people's approach in these past papers was to double the parameter space. So this Zhang and Wang et al. Papers, important early papers on this, and as you'll see, I really like this idea and picked it up in some later papers. So the idea is to double the dark energy parameter space, and instead of one parameter omega matter, have two omega matter for geometry and omega matter for growth. And likewise, if you have W as a free parameter, now you have two Ws. So practically in your theory equations, where you see geometry term, you feed W geometry, and where you see growth, you feed W growth. Roughly speaking, the geometry and growth quantities, theoretical quantities are these. This is a bit of a simplification. The simplest thing is supernovae, which measure distance, and the distance is all geometry. There's no growth. Now it gets more complicated. CMB, if you talk only about positions of the peaks, that's only also just geometry. Another simple thing is cluster counts. The number of clusters of galaxies is volume times number density. Volume is geometry, and number density is growth. Now, for some other things, it becomes more difficult to decide what's geometry and what's growth. And here I have some weak lensing examples. So this is a simplified picture. But the really nice thing about growth geometry split is even if you don't know if your term in equation is geometry or growth, it doesn't matter too much. Any choice mathematically works because you're doing consistency test of a model. I can make the following example. Imagine you split your data in data taken on Monday, Tuesday, Wednesday, and data taken, you know, Thursday, Friday, Saturday, Sunday, and you compare these two data sets. Now you may say that's a pretty silly split. Why would Monday to Wednesday be different from, you know, the rest of the week, every week? No reason, but those two should match anyway. You know, if they're all fair and square, they should match statistically. Now that's a not very smart split. You can do all kinds of splits. You can do, you know, by time, by other things. We think this is a very appropriate physically motivated split, because if modified gravity is at work, it would precisely make geometry not match growth. In other words, link between geometry and growth in GR is different if you have modified gravity. And this is exactly what we are probing. So we are measuring the difference in these two parameters, omega matter, growth matter. So we measure them together with measurement separately. This is a huge DES paper on the topic that, again, took several years to do. And my former student, Jessie Muir, did it. She's now at Perimeter Institute. She led it. DES did it. You know, there's lots of results and lots of validation. When the dust settles, this is DES alone. Sorry, this is DES plus external. This is year 1 data. This is older, not year 3. And you can see there's no evidence for departure. If there's departure, the standard assumption is this is 0, that these two match. But if they are not, you know, if you find a non-zero value, then in principle, either you found evidence for some kind of modified gravity or some systematics. Okay. So the next salvo in that was done actually by some people who I think are on the call now, Wendert Andrade and Rodrigo Van Martens. and Daya, the student who is now graduate student to Chicago, as well as Jalsul Alkaniz and I. So this is another project that took a couple of years, but we used not DES, but we used most other available data, including kids, to test this geometry and growth split. So basically we did, it's different from the Muir paper because some assumptions are different, in particular, some assumptions about modeling, which terms do you model as geometry and growth. So there's a sufficiently different number of assumptions. It's really a different kind of analysis. Oftentimes what you see in this split analysis is very weak constraints by individual probes. That you can see this red contour fills up all space. This is because this is a huge parameter space. In addition to all the usual parameters, you actually have twice the number of dark energy parameters. For example, you have 2 omega matters. So it's a pretty tough, yet when you combine the probes, you get good constraints. So it turns out one thing we found is that in our analysis, the difference between the omega matters, which is a perpendicular direction here, is very, very well constrained. Even though various other things are poorly constrained, this most interesting thing is very well constrained. You can see our tiny error bar. You can see maybe the universe is telling us something. There are many zeros here. We have a small error bar on delta omega matter. The difference in omega matter is because geometry and growth. And delta W also, which is 0 in the standard model, is also consistent with 0. So that's for the joint analysis. That's our result. But when we break it up between the different probes, again, here, it's hard to do one probe at a time because it's such a tough to constrain parameter space. So here we do dropping one. So this is all the probes but BAO, all the probes except for supernovae. So this is when you drop one at a time. And there we find that one case looks anomalous, which is the case when BAO is dropped. In other words, when you don't do BAO, but do all the other probes, you don't actually get the expected result, which is deltas to be 0. It's possible that you'll always get something to be off if you start looking at things. So there's that effect. This is probably some systematics. It's still early days, but I think it's going to be very interesting to see how this kind of result evolves as we get better data, especially as we, first of all, include the DES data, DES year 3, which is not public yet. It'll be public in January. And then also as we include in the future DESI data and such, and then space telescopes and etc. So I think these geometry growth tests will become really, really interesting, just because you'll have really different corners from which to look at geometry and growth and really tightly compare the two and see if they obey the relations imposed by general relativity. I think that's it. I would conclude that dark energy is a premier mystery in physics cosmology to this day. When I was in grad school, I started working on it. I thought it might be resolved in a few years, but that was now more than 20 years ago. That hasn't happened. There's a big, impressive variety of new data. There's this Hubble tension, which is great. It's really interesting. It's going to be interesting how it evolves and what happens to Hubble tension. I think the SCO3 data have established a new frontier in terms of quality and detail of analysis. I think that is definitely true. The results are consistent with lambda CDM model. I didn't mention, they confirmed this S8 tension, the fact that S8 in lensing is a little bit lower than S8 in CMB, not by 5 sigma, but maybe like 2.5 sigma. So that remains to be true. And then there's this X lens anomaly I talked about, which is probably systematic, but we'll see. One thing I also additionally talked about is this geometry growth analyses that I think will be very interesting in the future. That's all for the moment. Thank you.
Thank you very much, Dragan, for the remarkable talk. Now we have some time for questions. If you joined us on YouTube, you can put your questions on the comment section and I will redirect it to our speaker. And if you joined us on Zoom, you can raise your hand and ask it yourself. So, questions?
Sorry, how can I hand my, well, I can see how I can hand my hand.
Okay, go ahead. Go ahead.
Yeah. Hi, Dragan. I have a curiosity about what do you think about this blinding technique? Because I've heard that some people saying that it's not, well, fundamentally, in a way that the next survey, they will try to disprove the previous one. So there is no way to be bothered too much by this blinding technique, this blinding strategy. So I would like to see what you think. How do we should approach to new survey? If you do, you really think that it's necessarily a good thing to do the blinding?
Can you just, yes, I can answer. Can you just explain what was the reason given? What did you say the reason given against blinding was? The next survey will do what?
Yeah, you try to disprove, you know, they will try to find something different. Like the Planck would love to find something different from WMAP, for instance. So, yeah.
Okay, I didn't quite understand that reasoning, that they're going to try to find something different, but let me talk about this a little. I'm quite aware of this. So let me, a few things to be said about blinding. First of all, why do we need blinding? Particle physicists discovered this in the 1970s. You want to prevent yourself from jumping to conclusions, even if you are well-intentioned. Your brain will just jump to, you know, you will be debugging until you agree with the previous result, etc. I think the reason you offer it is that maybe you would actually like to differ with the previous. That's kind of like a dangerous psychological argument. I'm not sure that applies. But one other argument I've heard against blinding, which is very fair, is that first of all, this DES experience, we unblinded and then we spent 4 months messing with things because we had this anomaly. So isn't the idea that you unblind and you give up? So we mentioned what result we had after unblinding. We just tried to understand it. The idea also, I've heard criticisms that blinding is slowing down the team because you blind for some aspects of data analysis, maybe not key results, but some other, you need to actually look at the data to be able to tweak some things. So for example, for DESI, what we are doing now is we are not blinding a first small chunk of the data, but we may blind later. So the full story is a bit more complicated than, okay, you have to blind otherwise. And I agree with you there. I think this continues to be discussed. I think some kind of blinding is probably required for the key analysis, but it could be that this other things, like for example, what DESI is doing, the survey verification data is unblinded, I think. So anyone can look at it, play with it. So there's room for some middle ground when it comes to blinding.
Thanks.
Okay, thank you, Ander. Rodrigo, go ahead.
Okay, can you hear me?
Yes, can hear you. Okay.
So first of all, thank you very much for the seminar, Dragan. In the beginning of your seminar, you mentioned something on the H0 tension that you do not agree exactly with this early versus late description of the H0 tension. I was wondering why do you think why you have this opinion, and also I would like to ask about the SA tension and how do you see SA tension today? I mean, we have 2 dot something tension, but I don't know. It's somehow expected that 2 very different experiments observing different things with different systematics, they will not agree perfectly. And how do you see SA tension today?
Yes, sure. I can address these. Let me start from the second question. SA tension is here. So this is our S8. All the lensing surveys are finding 0.75, 0.77, and Planck measures 0.82, I think, just over 0.8. It doesn't sound like a big difference. You have to look at, when I was in grad school, sigma 8, like I said, this was 0.601, or 0.6 and 1.1. I think these were the boundaries. But the question is 0.6 and 1. Another case where it converged about 0.8, and now we are arguing about 0.77 or 0.82. But the error bars are much smaller. And I think I've heard you say is it might just be just expected. You know, if it's 2 sigma, there's nothing you can ever conclude about whether it's a normal statistical fluctuation. So this SA tension would have to become like 4 sigma for us to get really excited. Maybe that answers your question there. You know, right now that's why I didn't make a big deal out of it. Although people who do these analyses tell me in every lensing thing they look at, not just weak lensing, but this smaller scale people who do galaxy stuff, they find lower S8 effectively. So there may be something there, you know, that all of the galaxy things are showing you lower and the CMB showing you higher value. I think at this level, well, it's going to be interesting to follow what happens to it. But right now, there's no, it's just not at the same level of H0, I think basically for the reason you mentioned. To answer your, sorry, I don't know how to jump here, but I'm just gonna, to answer your question about Hubble, this early and late. So the argument goes that this is, I agree that local measurement of H0 is late universe because it's very low Z. But the question is the CMB measurement an early universe measurement? Because as you know, working on our paper, especially CMB has, of course, depends on the primordial things, primordial power spectrum, but then there's projection to the present day. And then projection includes some of the late universe. This is what makes a split not clean. In fact, I had a back and forth with Adam Rees on this a couple of months ago. He thought this was a good split, but I'm not sure I was convinced. You know, CMB just isn't cleanly early universe. There's this projection that comes from the late universe. That's all I meant to say on that topic.
Thank you. Thank you very much.
Thank you, Rodrigo. Wonder, you have another question?
Yeah, I have another question about the X-lensing tension or inconsistency that you showed. Can you go to that, please?
Yep.
So you put this extra parameter in the gamma two-point correlation function, but yep. the inconsistency on the parameter space it's when you, let me just see, you combine the two-point correlation function. So I was wondering why you just put this parameter on the gamma and in this two-point correlation function, and not in the angular clustering for position and only for shape.
Because this is how it works. This is a way in which it works. This is literally tuned to give you the biggest possible detection of X lens. So it's not a physical parameter. Is that what you're asking? It doesn't make sense. This is completely ad hoc. You want to decouple W and gamma T. You want to decouple them, and you decouple them by sticking. So you can stick a parameter in gamma or in W. I think you have that choice. It's equivalent. If you stuck it in W, it'd be greater than 1. If you stuck it in gamma, it'd be less than 1. But the point is to decouple the two. To break this relation between them.
But how can you be sure that this is coming from the shear two-point correlation function, not from the galaxy position correlation? How can you be sure that?
I didn't say it's coming from anywhere. I didn't say it's coming from anywhere. That wasn't the statement. This parameter, look, you can have equivalent parameterizations at work. You can stick it. I didn't say it's coming from anywhere. That would be like as if I knew the source of this. Mm-hmm. We have no idea where the source is. We're just saying if you stick a parameter, for example, here, I mean, it's not very surprising. If you have a 5 sigma off, you can devise a parameter that is a 5 sigma detected. I think that's just a mathematical exercise. So there's no new physics there. But no, I precisely never said it comes from anywhere. It's just that if you stick it somewhere at the appropriate spot, you will find it's detected. So it's a fairly trivial mathematical exercise. It's not new information. It's just confirming what we knew from the beginning, that something sticks out at 5 sigma. And it may help us, it may help somebody at this point understand the physics of why it's there. But we don't know which term it belongs to.
Yeah, I would think to do the other way around, just to see if it can be.
But you want to stick it into the shear or into the W? Where?
In the W.
Oh yeah,
the combination. It's, you know.
I think, I'm not sure, but I think it's literally equivalent to sticking in the W and having it be greater than 1. I think, but I think that's the case.
Okay.
Yeah. Yeah. Yeah, because it's the interplay between those two probes that makes for this weird result. So you want to break relation between them, and you can do it by sticking parameter at one side or on the other side. Yeah. I was thinking maybe this something has to do with the bias. You're not getting the bias correctly from the matter tracer. So I haven't worked on this, but I know people who spent 4 months on this and still know. So it's a really thorny bug, so to speak, right? But it's more like an astrophysical bug of some sort, probably.
Mm-hmm.
Yeah.
Yeah.
Okay, thanks, Wenda. More questions? Well, I have a very basic question from someone that is from another completely different field. All the science behind dark energy that you showed us has been done with photometric data. What will make DESI strong in this analysis? What is coming better from DESI, and how will it enhance the science you showed us?
Yeah, sure. I can talk about that briefly. I wouldn't say DES is all photometric, but it's not true that dark energy is photometric. I think, sorry, I don't know how to jump here. This is the relevant plot, this plot here. And this blue, sorry, it's covered up by, let me do this. This blue contour called BAO. So this is basically this baryon-acoustic, it's a feature in galaxy clustering that's effectively a geometrical information. You need a spectroscopic survey to measure that feature. This is the part that DESI will do better because it'll have bigger redshift, more galaxies. So you think about this green contour shrinking. It's going to do one other major thing, which is called redshift space distortions, which is the way galaxies cluster on small scales is anisotropic. It actually is not isotropic, and that's a more difficult to model thing. So BAO and what's called redshift space distortion RSD, which are not shown in this figure. But the simplest way to think about DESI, like this absolute zeroth order, is more galaxies for this BAO feature, which is predicted with no. The theory is perfect for BAO feature. It's known to exactly. It's a linear theory calculation. So you just need to measure excess clustering at 100 megaparsecs. And so you think about this green contour shrinking by a lot. That's what it's going to do. And then, of course, for geometry growth and many other kinds of tests, you can also use the. Also, here's in this Hubble diagram, I think here I have a few effective BAO measurements. So it turns out when you measure that feature, these red points, you effectively measure a distance. You're measuring a distance to this geometrical feature, this ruler, that's 100 megaparsecs. So the other side of a triangle is known. And you measure angles, so therefore from a triangle you get the distance. So there are 3 distances now, 3 or so. And so DESI is going to get, if you think about these red points, imagine a few more such red points to higher Z, to Z of 2, with maybe slightly higher density. That's what it's going to do. That's like the zeroth order thing. Yeah.
Okay, that sounds really great. Well, thank you. We still have time for a last question. Okay, Wender, go ahead.
If nobody has another question, can ask. Okay. Just a curiosity, you mentioned that when you get the covariance for your data, the covariance matrix, you usually don't do simulation like mock, you just get it from theoretical covariances. So I was just want to ask you, just to check, understand, is that really true? You don't simulate any covariance for the DS, this is only from theoretical that you get?
Yeah, it's not true in detail. When that's a good question. Roughly speaking, it's theoretical because good luck in running enough simulations to get, maybe for smaller number. I mean, this is something that people are exploring. For example, doing this, what is it called? Not condensing, but projecting to a smaller number of observable quantities. If you have a smaller data vector, say 20 by 20, then you can imagine building enough covariant simulation runs to numerically construct it. But if you have 1,000 length data vector, you have to do theoretical. We do use some cheap and quick numerical simulations to calibrate certain terms in this covariance. And this is not my area of research. I'm not super familiar, but roughly speaking, it's true. So there's another 30-page paper, one of those by Oliver Friedrich, that has all the details about this covariance that you ever wanted to know. The thing about covariance now that you asked is even though it's fundamentally relatively complicated, First of all, the Gaussian assumption for the likelihood analysis, it works very well, which we should be grateful to the gods of nature for arranging this for us, because going non-Gaussian will be more complicated. And then this theoretical formula, also theoretical modeling, seems to be accurate enough. And this further calibration by some simulation also seems, so everything seems to work out just fine, at least for DES. I don't know if that's going to be the same true for future surveys. But yeah, to answer, yeah, again, we do calibrate some terms with numerical work.
Yeah, just asking because I've seen like BOS, Z-BOS, like they run some unibody simulation, things like that to access also to compare the covariances with theoretical modeling.
Their data vector is much shorter, as you know. They only have they project to only a few distances and few, so they have like a 5x5 data vector that you can do. But we have a richer set of observables, so at least the way we are doing it now, we can't quite do the same.
Okay, thanks.
Thanks, Wonder. If there are no more questions, I think we will now wrap this up. This presentation will be available on our website and on the YouTube channel. And a quick announcement for the next week's webinar, we will have Nina Hemstedt from the Vanderbilt University, continuing our series about the LSST alert brokers. So thank you everyone and for attending, and a special thanks to Dragan. Dragan, thank you very much for giving us your time and this remarkable talk.
Thank you very much, Rodrigo. Thank you everyone. Thanks for coming. It's been a pleasure. Take care.
Thank you very much. Everyone, have a great day. Stay safe, and I hope to see you all again next week. Thank you.
Bye-bye.
Bye-bye.